This video is going to talk about a proofwriting technique in geometry called superposition. Superposition is at its very basic level where you take some geometric object that you care about and you move it to somewhere else in your plane. And plane is simply the technical term for, in classical geometry, your flat piece of paper that you're working on. So it's literally the geometry of where you're living. Okay? Now, in terms of what we're doing here, we are looking at a little bit of behind the scenes. So for just a second, we're going to take a brief aside and look at some of the very technical details. If you don't understand all this, don't worry about it. Hold on, we're about to get to the example of how to use superposition. So what this concept of being able to use superposition means is it means there's something called a homogeneity of your geometry. And homogeneity is just talking about that the geometry acts the same wherever you're at in your plane, if you're in a two-dimensional geometry. Okay? Now, this is highly related to something also called rigid motion. And if you notice here under that first sentence that's just flew in, that looks like the exact same thing of superposition. And it is. It's basically a different part of speech, whether you say rigid motion or superposition. A little bit more complicated than that, but hand waving through, that's perfectly fine for right now. So here's some of the technical details. Rigid motion is a one-to-one transformation where points in your plane, so remember that's any point that you could draw on your flat piece of paper, gets mapped to some other point in your plane or in your flat piece of paper. Now, here's the criteria that makes sure that that one-to-one transformation actually works how we want it to work. In other words, you're able to copy one geometric object from wherever it's currently living to anywhere else in the plane and still have an object that's congruent to your first object. What you need to do is, if you start off with a straight line, all of those points in your straight line, you typically think of this as a straight line segment, will get mapped to a new straight line segment where the new straight line segment is congruent to the old one. So it's the same length. Okay. Same deal with angles. If you have an original angle, all the points into that angle are then mapped to a new angle that is congruent to the original or has the same degree as the original angle. Now, what does this mean in terms of that one-to-one transformation? Remember, a transformation is a type of function. So what do you have? When you plug in points, you get back points. You can also rotate your points about any point. That means if you plug in array, you should get back array. You can also, by using this one-to-one transformation, you can reflect your geometric object, i.e. all the points contained in your geometric object, about any line. Now, you guys have all done this before if you've done pretty much anything in high school math. So the example here is in R2, so think in your head XY coordinate plane. Here, if you're talking about rigid motion, you're looking at, and picture in your head maybe like a function back in an algebra class. This would correspond to translations, rotations, and reflections. This is way back when in typically high school or a freshman level college class, you're looking at where you are literally moving your functions up and down, right and left, side to side, maybe reflecting them and spinning them around. This is that same stuff, except now we're not focused only on functions in the XY coordinate plane. We're doing it in the more abstract into our geometric objects. So let us look at a proof of a theorem that uses this technique of superposition, that uses this rigid motion, if you will. Okay, so what we're going to do is we're going to look at the validity of the triangle congruence theorem of right angle side side. And remember, right angle side side was the corollary of proposition 26 from Euclid's first book. So what that means is, remember, when we're proving things, we're not going to use anything that's higher than the number of the item we're proving. And if it's not something that Euclid talked about, you should be given what propositions you're allowed to use. So like, for example, in your homework, you'll often see a problem that you're asked to prove that's not necessarily one of the propositions in Euclid's books. And then in the directions in either your textbook or otherwise, it'll say, hey, you can only use proposition 1 through, and it'll give you a stopping point. Okay. All right, so back to right angle side side. In terms of right angle side side, we're going to start off with two triangles. I'll go ahead and name these triangles ABC and DEF because I'm super lazy in my naming conventions here. And what do we know about right angle side side? We have to have a right angle in each of the two triangles. Here we've gone ahead and chosen the angle B and the angle E in these two triangles to be our right angle. and we have to have the hypotenuses congruent to each other. So that's AC is congruent to DF. And lastly, one of the legs are congruent across the two triangles. In this case, I lazily picked on AB and DE in the two triangles. So that's our given. That's where we're going to start with our proof. Now, as it currently stands, the two triangles, how they're currently written on the plane, notice here, they're just two triangles flopped down. There's nothing wrong with how they are, but it's not useful in getting the information that we need, which is to say that these two triangles are congruent to each other. Now, reminder, two triangles are congruent to each other if all three of their angles are congruent across the two triangles, and all three corresponding sides are congruent across the two triangles. So we need to get that the third side here that we have no information about are congruent. We also need that the two pairs of remaining angles are also congruent. Now, proposition 26 is quite a bit after some of our other propositions, so we can use anything before 26 just fine. Okay? So let's put this in a T-chart. First thing that we're going to do is, and I went ahead and skipped on writing this given statement here as the first line, but technically we should have gone ahead and put this all of this stuff that we just said given up here in this very first line. Okay, I'm just illustrating another way that you can do it right here. So first thing that we're going to do is we're going to go ahead and we're going to extend this line FE out, and we're going to extend it in such a way that we'll then copy BC onto the extension of the line FE, specifically on the left-hand side here of point E, or opposite side of point E than point F is. Okay. What this does is we're going to end up with EG being congruent to BC. Note the citation. Proposition 2 in Book 1 of Euclid is a specific way of copying an angle. Specifically, you've got a line segment that you've copied this angle onto. Now, once we have that extension right here, the side EG that we know is congruent to BC, we're going to go ahead and attempt to copy this triangle ABC right over here on this left-hand side of our triangle DEF. So we'll just go in and connect the 2 points D and G together. Cite this with our construction step of postulate 1, which says any 2 points you can construct a straight line that contains those 2 points. Now, at this point in time, we are assuming that we've just copied triangle ABC to DEG, but we need to verify that everything actually worked correctly. In other words, we need to verify that triangle ABC is congruent to this new one we just created, DEG. So let's go ahead and do that. So I'm going to go ahead and claim that the angle there at E, that new angle at E, is a right angle. We need this to be a right angle because we already had a right angle up here at B, and there's no way these two triangles could be congruent if we didn't have a second right angle at E down there. Now, this citation here of postulate 13 in book 1, it talks about supplementary angles. Notice here in the previous, well, not previous step, but the 2 steps before, when we extended the line EF, that meant we had a single line that contains F, E, and G. So we have one line and a second line standing on it. Now that we have one line standing on another line, we have supplementary angles. We already know that the angle E here, DEF to be precise, was a right angle, which means automatically DEG also has to be a right angle. This also ties into the definition of what a right angle is. Right angles tied very closely to when you have one line standing on another. It's more precise than that, but they're tightly aligned. Okay. Now, next thing is I'm going to claim that the angle at B, the angle at DEF, and GED are all congruent to each other. Postulate 4 says if you've got right angles, all right angles are congruent to each other. And by this point, we've already established that those 3 angles are all right angles, which means we can then apply side angle side. Now, side angle side is in Euclid, and it is proposition 4 in Euclid, which means it's totally fine to use right now because we're working on something up near proposition 26. So we can use side angle side. Notice where that is. Side angle side is DE is congruent to AB. That's something that we knew already. We just established that B and E are congruent to each other. There's the angle part. And the second side is the one that we forced. This is EG and BC are congruent to each other right there. Okay? So this now tells us that we have a copy of triangle ABC at DEG. Now, why do we care? So here's the y over to the side. Okay. Notice what we just did. First thing we did was we copied the triangle ABC. So ABC is congruent to EDG. Now, second thing we're going to do is we're going to show that triangle DEF, that's the second original triangle that we have, we're going to show that it is congruent to DEG. It would be extraordinarily difficult to show that the two original triangles are congruent to each other without this helper triangle we just copied. And then, conclusion, we're going to get that triangle ABC is congruent to triangle DEF because of common notion number 1. And remember, common notion number 1 says if you've got two different things congruent to the same third thing, all three of those items are congruent to each other. So this, in this situation, is why we care about copying that triangle ABC to its helper location. So let's see if we can't show that the new triangle and the original second triangle of DEF are in fact congruent to each other. So we know a couple of things already. Right now we know that we have the two angles at E are congruent because they're both right angles. We know that we're sharing an edge right here at DE, so that's congruent to each other. But, and here's the other part, we don't really have much information about the other sides of the triangle. We do know that the triangle DEG is congruent to ABC, so let's see if that'll help us. And I'm going to claim that the very next thing actually does use the fact that DEG is a copy of triangle ABC. I'm claiming that DG is congruent to AC. So notice hypotenuses congruent to each other. Why? Corresponding parts of congruent triangles are congruent. Okay? In other words, definition of congruent triangles. Now notice what this gives us. This now gives us that we have a pair of sides are congruent, another pair of sides are congruent because it's the same side, and then a pair of angles are congruent. But if we actually only looked at what we currently have, this would be side, side, angle, or as some people like to call it, angle, side, side. And this guy here is unfortunately not a triangle congruence theorem, which means we have to find some more information because as of right now, we don't have enough to do anything with. Okay? So let's check out something else. And this something else is a trick about where we moved our copy of triangle ABC. Notice what we did with it. We actually put it right next to our triangle DEF, and this forced us then to have a larger triangle. Now notice something about the larger triangle. That larger triangle is isosceles, and we know it's isosceles because we literally just went ahead and said that these two angles are congruent to each other. Now, with the hatch marks, we can see they're congruent, but notice you do need to have one little lead step here that says, hey, DG is congruent to DF by common notion number 1. And just a reminder, why did we have that? Because AC was congruent to DG and DF was congruent to DG. I lie. We had DF is congruent to AC. And that gives us that DG is congruent to DF. I jumped ahead there for a second. Alright, which means we now have isosceles. Okay. Now, once you have an isosceles triangle, you can use any properties of isosceles triangle you want. So here, what we're going to do is the standard property of isosceles triangle, which is that your angles opposite your congruent sides are in fact congruent to each other. And this is down at proposition 5. It's somebody will use all the time. So definitely star it big time to say, hey, I love using this guy, but fair warning, it does not have a special name. Okay. So we now have what? We now have an angle F, angle G are congruent to each other, and we've got a bunch of sides that are congruent to each other. So we look to see what we have, and we check to see, is there a triangle congruence theorem that we can now use? Okay. And the answer turns out to be yes. Okay. So take a second, put this video on pause, and see if you can't spot the triangle congruence theorem that we're about to use. All right. So, assuming that you guys have now thought about what triangle congruence theorem we're about to use, hopefully you guys are all thinking angle, angle, side. Now, why would I say angle, angle, side? Because we're looking at what, guys? We're looking at the shared angle right here of DG is congruent to DF. We're looking at the angle we just grabbed, which is G. Angle G is congruent to angle F. And we're also looking at the right angles are congruent to each other. So there's two pairs of angles are congruent to each other, plus the hypotenuses of these two smaller triangles right here, which is the side that is not between the two angles. Now, remember, right angle side side was a corollary of proposition 26. One of the things that you get with a corollary is it's a direct result of that proposition that it's a corollary of, which means we have to use proposition 26 from Euclid's first book in this proof somewhere, otherwise we wouldn't have gotten a corollary. Angle, angle, side is one of the things that you get out of proposition 26 from Euclid's first book, which means, bam, we've just used proposition 26. We are basically almost done with this proof. So what have we showed so far? So far, we've shown that our helper triangle DEG is congruent to triangle DEF. We already knew that triangle DEG, that helper triangle, was a copy of triangle ABC. So we can put that all together and link it with common notion number 1, which is roughly transitivity, and say, hey, well, our helper triangle helped us out, so now we can say that the original two right triangles are in fact congruent with each other. And that is a way to use this technique of superposition. Basically, you had one of the things you needed to use. It wasn't in a good spot, so you moved it to a good spot, and then were able to do your proof like normal.